Hi, Chuck Huber here for the Stata YouTube channel. Today I'd like to show you how to use extended regression models, also called ERMs, to fit a linear regression model. This is the first in a series of videos in which I will work the example from Intro 8 in the ERM manual. These videos will show you how to use ERMs to fit models that account for endogenous covariates, non-random treatment assignment, and endogenous sample selection. You can download the ERM manual at this website if you would like to read the entire example. This video will focus on endogenous covariates. A covariate is endogenous if it is correlated with the error term. Endogenous covariates can be caused by, among other things, omitted variables that are correlated with the other covariates in the model, the covariate is measured with error, or reverse causation of the dependent variable and a covariate. I'll be using a simulated dataset called Wellness, and you can download the dataset by typing WebUse Wellness. You can also view a list of the variables by typing describe. This dataset contains information about a wellness program offered by a large company. We are interested in the effect of a wellness program on the amount of weight lost by employees. The treatment variable is WellPGM, which is an indicator for participation in the wellness program. The dependent variable is weight loss, which is the observed number of kilograms lost by each employee. Because these are simulated data, our dataset also includes the variable weight loss 0, which is the true amount of weight lost and is determined by this equation. In practice, we would not observe weight loss 0, but we have included it here so that we can compare our models to the true model. We can fit the true model using regress and estimate the average treatment effect of WellPGM on the true weight loss variable weight loss 0. The estimated coefficient for WellPGM tells us that the average weight lost over the course of the year would be 1.25 kilograms greater if all of the company's employees participated in the program versus if no employees participated. Here I'm going to type estimate store true so that I can refer to these results later. Now let's assume that I only observe the variables listed here. I can use regress to fit a model that is similar to our true model using the observed dependent variable weight loss. Notice that I do not observe the variable health, so it's not included in the model. Let's store the estimates from the base model and compare the estimated coefficients to our true model. There are several differences between the two models. The true model with the dependent variable weight loss 0 includes the covariate health. The baseline model with the observed dependent variable weight loss does not include the covariate health. Our true model has 545 observations, but our baseline model has only 337 observations. And the estimated coefficients for our baseline model are also different from our true model. In particular, the coefficient for WellPGM is 1.91 in our baseline model, which is higher than the coefficient in the true model. Let's focus on the omission of health from the model. People who are predisposed to healthier behavior are likely to have a lower starting weight. This healthier behavior may also influence the amount of weight lost. Since health and weight are related, weight is likely to be an endogenous covariate. We can model an employee's starting weight as a function of sex and the variable gym. Here, gym is the average number of monthly visits to the company gym before beginning the wellness program. Here, gym serves as an instrumental variable. An instrumental variable is an exogenous variable that's correlated with the endogenous covariate but not directly related to the outcome or the unobserved errors. We can fit this model using eRegress. So let's begin by selecting Statistics, Endogenous Covariates, Models adding Selection and Treatment, and then I'm going to click Linear Regression. In the Model tab, we begin by selecting the observed dependent variable weight loss and the independent variables age, sex, and WellPGM. Next, we check the box next to endogenous covariates and click the Create button. Here, the dependent variable is our endogenous covariate weight, and the dependent variables are sex and our instrumental variable gym. Weight is continuous, but we could select probit if our endogenous covariate was binary, or ordered probit if our endogenous covariate was ordinal. Next, we click OK, and then OK again to fit our model. The dialog box runs the command eregress with the dependent variable weight loss, followed by the covariates age, sex, and well-PGM. So that's our main equation. And then our equation for our endogenous covariate weight is a function of sex and gym. Notice that our output contains coefficients for two equations, one for the main model with the dependent variable weight loss, and the second for the endogenous covariate weight. At the bottom of the output, we see that the estimated correlation between the errors of these two models is minus 0.497. The p-value for this correlation is 0 and indicates that weight is in fact an endogenous covariate. Let's store our results by typing estimate store endog and compare our parameter estimates with the coefficients from our true and baseline models. Once we account for the endogeneity of weight, the coefficients for sex and weight are closer to those of the true model. But unfortunately, the estimates for age and well-PGM are still different than the true values. This difference is partly due to non-random treatment assignment, which I'll cover in the next video in this series. I hope this was helpful. Thanks for stopping by.